Hello and welcome to another LeetCode problem. So today we're going to be doing the problem of the day for June 15th, and it's going to be maximum level sum of a binary tree. So the problem is, given a root of a binary tree, the level of its root is 1 and the level of its children is 2 and so on. Return the smallest level x such that sum of all the values at level x is maximal. And so for this example, what we are going to be doing, pretty straightforward. So a level means all the nodes that are like the same way down. So like this is a level, this is a level, and this is a level. And so we can actually just write out the sums on the right here. So for this level, the sum would be 1. For this level, the sum would be 7. And for this level, the sum is -1. So it's just saying return the level that has the biggest sum. So clearly here it's this level here, and then the levels are one index, so this is level 1, level 2, level 3. So we would return this one here. Okay, let's look at the next example. So we have 989. Hopefully I draw this correctly. Okay, so null I think means that you have no left node. So then this is 10,250. Okay, and then this is 9,8. 6, I guess these are, yeah, I don't know why they use this example. It's definitely not the best. 693. Then I think it's like this, -8, 9, 3, 8, and then null, 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 and then here is -32,000 something. Okay. So clearly, it's not super clear, I guess, but so the sum here, let's just look at this. So for this level, sum's 989. Okay, the sums here is 10,250. Sum here is negative, so we're just going to ignore that because that can't be our answer. And the sum here is around the ballpark of 9,000 something. Not sure exactly. Like, I think it's like 9,000 whatever, 6. Let's just call it 9,600. It's not exactly it, but close enough. And so we need to figure out our greatest level, and so that's going to be this level over here. So remember, this is level 1, 2, 3. So we want to return level 2. All right, so now that we kind of know what we're asked to do, how do we solve this problem? So for a binary tree, what you're actually going to want to do, let's draw this first one again, is when you're doing levels, it's pretty straightforward. You're going to want to have some way to like know what level you're on in some way. And so there's two ways to do this. You can either do a breadth first search, which is the more popular way to do it, where you go down level by level. So like you have a queue, and so you have like this node in the queue, and then you go down level by level to its children. So you would go down to the children of this 1, which would be the 7 and the 0. And then you go down the next level, which would be 7 and -8 and so on. So you pretty much take every single node in the queue, then you go down to its children, and then for each level you can just take the sum, right? So like we'd get a sum here, we'd get a sum here, we'd get a sum here. So that's one way to do it. I'm not going to do it that way. I am pretty stubborn, and I am a bigger fan of depth first search than breadth first search, so we're going to do it that way. And so the way that's going to look is pretty straightforward. So for depth first search, let's make this bigger again. It's pretty straightforward. So what we're going to do is we're going to have a function that accepts a node and a level. And it's going to be a recursive function. And then we're going to have some output array that's going to have all of the sums on each level. So it'll just start with a 0. And then pretty much what we're going to do is, like, let's say we're at some node like this. We're going to say, okay, well, is our level in, like, is our output array long enough to add the level or the node's value to the current sum that we have? And so for this, for example, this is length 1. So if we're at past length 1, then we're going to have to add something, but I'll show you how that looks like. So we're at the first level, so we're going to say, yeah, this is long enough to add a value. So what we're going to do is we're going to take our node's value, which is at node 1, and we're going to add it to the sum of that level. And so we're going to just do this. So this will get updated to a 1. Now we can either go left or we can go right, doesn't matter. So let's say we go left. Let's say we do node, we get the node's value, and then we go left, and then we go right. It's totally fine. You could do whatever way you want, it doesn't really matter. So we're at this node 7, and then our level is increased, right? So initially we were at node 1 level. I'm going to have the level 0 indexed. So we're going to be at node 1 level 0. Then we go down to node 7. Every time we go down, we increment 1 to the level. So now we're going to be at level 1. And so we have the 7, and we ask ourselves again, okay, is our array long enough to handle this level 1? Well, clearly it's not, right? Because this one, so all these levels are going to be 0 indexed. So this is going to be, this one is at index 0, but I need to add something to the sum at index 1. So it's pretty straightforward what you do if your array isn't long enough. Also, what you could technically do if you really wanted to is instead of making this array 0, what you could do, you can't have any more levels than nodes in the tree, or right, like worst case scenario, all your nodes are like this. So what you could do if you wanted to was you can make your starting array length n, where n is the number of nodes. I'm not sure if they give that to you. No, they do not. So actually, you can't do it that way. But it's pretty easy to add as you go. So anyway, so we're at this level, and we ask ourselves, like, do we have a slot here for the sum? No, we don't. And so as long as we don't have the slot, we're just going to keep adding zeros into this array, because all these sums are technically like 0 anyway. So we're going to keep adding zeros into this array until we do have a slot to add the 7 to the sum. So now that we do have a slot, we're going to add 7 to it. Then that's going to turn into a 7. Now let's say we go left, right. So we're down here, and this is at level, so 0 index, this would be level 2. So level 0, level 1, level 2. Then we say, okay, so we're at level 2. Can we add this value to over here? Like, do we have a sum value? Well, we do not. So we're going to add another 0 here. And then we are going to add the 7 to it. So I'm actually going to make some space for that. So we're going to add the 7 to it, and then that's going to be a 7 now. Then we recurse back up here. Recurse back up here. Now we go to the right node, so it's going to be level 1 again. And so this is value 0. So, but once again, we say, can we add this to the sum at like the level in this? And we can. There is a level there. So we just do 7 plus 0, which would be 7. Then we recurse down here, and we say, can we add this to the level? Yes, we can. This array is long enough. So then we do 7 minus 8, which is -1. Okay, so now we have this output array of 1, 7, -1, and this is corresponding to the levels. So this is level 0, 0, 1, 2. Now remember, the levels they gave us are 1 indexed, so it's pretty straightforward. We can just take whatever index we are at. Like if this is the maximum level, we just take whatever index we're at and we add 1 to make it like what they wanted in the actual question. But pretty much now we have to traverse the array. We have to get the max like element, and then we have to return the index. So whatever index I plus 1. Now there is an edge case, which I'm honestly not sure that they tested for it, but I definitely make my code to handle it. And so they're saying, return the smallest level x such that the sum of all values of nodes at level x is maximal. So it is kind of weird phrasing, but what I interpreted that as is like, if you have some levels like this, you're going to want to return the smallest level that has the maximum sum. So if multiple levels have the same sum, you're going to want to return the smallest level there. And so that's going to be pretty much our algorithm. We're just going to do a depth first search through the tree. We're going to check, is there a level in the array? And if it is, just add the current value to the sum. And so that's going to be like an optimal solution. And I don't know if there's any way to do it without having some kind of array, because if you do a breadth first search, you would also have to store nodes. You would have to store the nodes at your current level, which would be also, you'd have to, like, it's going to be on the same order of things you're storing. Because, yeah, I mean, maybe it'll be a little less. No, I think the order will still be the same. Okay, so we're going to do this depth first search. And so we're going to make a helper function. So let's call it maybe traverse. We also do need a... let's call this sums maybe array. And that's going to be, I'm just going to initialize it to this for now, and then I'm going to add zeros like I showed if we need more levels. So we're going to do this, def traverse, we're going to have a node, and we're going to have a level. So if not node, in this case, it's okay for us, for this function to go into null nodes. If we go into null nodes, we can just return. So for some functions, ideally, you don't want to go into null nodes, and then you can check beforehand, but in this case, it's fine. Okay, so now remember, we have to, we can do this either way, it really doesn't matter, but what we're going to do is we're going to add the node's value into the sums array, and then we're going to go left, and then we're going to go right. So if level is, and then here, so remember this level is going to be 0 index, so if level is greater than length sums minus 1, because here the length of sums would be 1 and level would be 0, so if 0 is greater than 0, that would not be true. But if we were on level 1 and this would be length 1, then it would be if 1 is greater than 0, we definitely would need to add another level. So if the level is greater, actually this should be not if, this should be while. I think technically an if would work, but let's leave a while just in case. Okay, so we're just going to keep adding zeros to the... I think actually a little bit more efficient code is, I think this can be an if, and technically you should only have to add... Yeah, I mean, let's just try to do it optimally this time. I'm lazy usually, but let's just do this. So technically, I think when we're at a new level, we should always be at one level, at a level that just... We only need to add 1 0, right? Because if we're at this... We came from something that already was added into sums. So because we can only traverse down one level at a time, technically we should only have to add one value here. So we can, I think, do something, save a little bit of code and just literally do this. Because basically the length of this sums, worst case scenario, is only one less than what we need. And so what we're only going to do is add 1 0 and then add this value to the 0, which is the same as doing this code. Okay. So that's that. Now we need to go left and then we need to go right. So traverse node.left. And like I said, it's okay to go to null nodes and we have to add a level here. And then traverse node.right. We have to add a level here. Then we need to call our function. So traverse root, put that level 0. And so now we need to have the result and we need to have the index of the result. So for the result, we're trying to maximize it. So we'll just make that negative infinity. And then for the index, we'll just make it -1. We should always get a valid index here. So then for index value in enumerate sums, if the value is greater than result, then we need to update the index to be the index, and we need to update our result to be the value. So as index equals I, as equals v. And now if we do have two numbers that are the same, let's say we have a 7 and a 7, so the first time the 7 will be greater than the result, we're going to update this, but then if we hit a 7 again, then it won't be greater than the result, so this index will be the same. So this will ensure that we get the first level with the maximum value. Okay, I'm going to return, so we need to return res index, but remember our code was 0 index and they want it to be 1 index, so we're going to need to add 1, I think. So in our code, level 0 would be level 1 in here. So let's see. Interesting. Let's debug this real quick. Okay, so if level is length of sums. Okay, first of all, let's just print the sums just to make sure we're actually getting that correctly. Okay, so yeah, so we definitely want this value. So let's just, so we're doing some kind of mistake here then. Okay, so if v is greater than result, res index equals I, res equals v. So our result is negative infinity, which should be fine. And then our sums is being printed out correctly, and we would want 2. Why are we getting 3? Interesting. Yeah, so this should be index 1, and then we should return this plus 1, I think. Yeah. 10. Actually, no. Hold on a second. No. We would want to return. Let me look at. I don't think I have that picture saved, but let's see here. For case 2, we would want index 2. Yeah, we do want index 2. So maybe we actually did something wrong in our calculation. Yeah, we are. Yeah, we definitely are doing something in this thing. Okay, so that's good to know. Because this should be 1 and so on. Yeah, so this is definitely wrong. Okay. That's good to know. Oh, right. Okay. So, easy solution. So, we did check if our level was out of bounds, but then if our level is not out of bounds, we need to... Yeah, so let's just do this then. Yeah, so basically it was, if our level was not out of bounds, we never actually put the value in. So this should not be sums.append, this should just be sums level. Okay. So this should, I think the ifs here should technically work, but the okay. All right. Yeah, so this can only happen one time max. So yeah, the problem we had is if we had a node that was actually at a level, like let's say we have this 1, it'll be fine. But and then we go to the 7 and we are gonna add the value, but then we come over here and then that level did exist. We never appended this value because we only said if the level does not exist, create it. But if the level already did exist, we never actually added the node there. Okay, so let's do the time and space complexity here. So for time, we are going to every single node. So that's going to be big O of n is the number of nodes. And then we are also enumerating the sums, which is also going to be big O of n because we're going to have a worst case scenario. We're going to have n levels. Like I said, if it's this kind of thing, like then every node will be on a different level, but that's not adding any time complexity. Yeah. And then space. So we are going to have a sum for every node, which, like I said, worst case scenario, and also our recursive call stack worst case scenario is length n, because if it's like this, then you're going to start here and you're going to have to recurse all the way down before returning, and so you're going to have to save this whole like recursive call stack. So this is going to be big O of n as well. Yeah, and that's it for this problem. Hopefully you liked it, and if you did, please like the video and subscribe to the channel. It helps grow it a lot. And thanks for watching. I'll see you in the next video. Bye.